Hi, my name is Yara Bahram, and today I will present to you our work DogFit. So diffusion models are great, but in practice, we often want to adapt a big pre-trained model to a smaller target domain with limited data. For example, in this 2D case, the target domain is the small red region with 3 samples from 2 classes, the square and the circle. Fine-tuning source pre-trained models on the target domain will often result in poor generalization, generating misaligned data like the black square that we see here. Assuming that we are in the noisy image space, if we were to denoise x of t using class conditional noise estimation, it would likely shift toward this red direction. However, in the unconditional case, the estimation would shift the image toward the closest region in the target distribution, the blue direction. Classifier-free guidance, by computing a guidance offset derived from the conditional and unconditional noise estimates, provides a model with a better class condition alignment and generalization. A guidance weight can be utilized to control the amount of guidance, giving a natural fidelity diversity trade-off. However, there are 2 problems with classifier guidance in transfer learning. First of all, it requires 2 forward passes for each denoising step, as it requires both the conditional and unconditional estimates to compute the guided direction. Further, the unconditional estimate is weakly defined. It can cause the model to go toward directions that lie outside of the target domain manifold, producing out-of-distribution data. Further, this unconditional estimate is weakly trained since the target domain is way too small for conditional dropout training. Model guidance tries to eliminate the double forward pass problem by directly learning to predict the guided direction without computing the guidance offsets. However, a new problem rises. The model loses its test time guidance control, since the guided weight is now hard-coded into the model. One way for better target alignment is to use the source model as the unconditional estimate, leading to the domain guidance method. So the question is now, can we learn a target-aligned direction like in domain guidance with only 1 pass sampling and no guidance offset prediction, while being able to control the fidelity diversity trade-off at test time? Leading us to our method DogFit. At its core, DogFit is interested in simplifying the sampling process of domain guidance. DogFit uses the same old diffusion MSE loss during training while adding a domain-aware offset to the target noise. The conditional estimate is provided via the learning target model and the unconditional estimate via the source model. We further use a stop gradient operation in order to prevent collapse. DogFit also keeps what people love about guidance, controllability. We treat the guidance scale value as an additional input condition during fine-tuning, so at inference, we can dial the value up and down for the usual fidelity diversity trade-off. For this, we sample a guidance weight and then learn the relationship between the unguided and the guided model in a self-supervised manner. Interestingly, under mild assumptions, training with DogFit makes the model replicate domain guidance behavior for any guidance value. To fulfill these assumptions, we choose to sample the guidance value during training via a shifted exponentially decaying distribution. This lets the model focus more on small guidance values around 1, while occasionally exposing it to larger values, increasing robustness to larger ranges during sampling. We further find an interesting relation between DogFit and model guidance. DogFit adds a domain alignment component to model guidance that pushes samples toward the core of the target domain manifold and away from the source, helping avoid out-of-distribution artifacts. On the left, you can see how the training of DogFit is done on diffusion transformer architectures, and on the right, you can see how the guidance weight can be incorporated to the network for test time guidance control. Experiments are conducted on 2 diffusion transformer-based architectures, starting from a source model trained on ImageNet transferring it to 6 target domains with diverse characteristics. We use FID and FTDyno on the target domain for quality evaluation. When considering both the sampling cost and quality, DogFit often outperforms other guidance methods, performing competitively in all cases. Qualitatively, DogFit generates sharp domain-relevant details, often with less visible artifacts seen than the other methods. Note that FFHQ is an unconditional dataset for which classifier-free guidance does not produce any results, since there is no conditional estimation. However, because of the implicit domain alignment term, domain guidance and DogFit are able to produce guided images in these domains. Importantly, when the model is trained on guidance value conditions, we can sweep the guidance value at inference time and move along the fidelity diversity trade-off. However, overexposing the model to overly large guidance values during the training can break the performance and collapse the model generations. This is represented by the quacells. We also find out the timing and the placement of the guidance matters. Specifically, we find that skipping the guidance during the first training iterations as well as the first denoising steps allows the model to reach better performance and stability during training. Therefore, we propose 2 simple guidance scheduling mechanisms: late start and cutoff. Our revelations cover testing the robustness of DogFit under a varying number of sampling steps, showcasing the orthogonality of DogFit with parameter-efficient fine-tuning methods, and comparing the shifted exponentially decaying distribution for sampling the guidance value with uniform sampling across different ranges. To wrap up, we propose DogFit, a controllable guidance mechanism for diffusion transfer learning that improves target domain alignment without needing double forward passes at test time. We show that during fine-tuning, the source model offers stronger marginal estimates than the learning target model, making it better suited for generating guidance signals. For transfer learning across 6 target datasets on DIT and SIT methods, DogFit outperforms state-of-the-art guidance methods in majority of cases while being up to 2 times faster. Thank you for listening to this talk.